Welcome to today's live stream. We have Nick talking about what are you talking about today, Nick?
Just showing some pretty pictures, talking about quantum geometry,
All right.
and also questions about it. Hoping Cowers will answer them, or at least we're just gonna speculate. So let me start sharing.
I'll do my
Yeah.
best.
So the topic was Cubix from Qubit, right? This is just to remind us. I already showed this particular picture, just to remind someone who already seen that, where the cube is, how the cube is appearing in the qubit geometry, right? We were like we're showing this cube in the qubit as like just a combination of two special phase space bases, essentially. Just you can construct two tetrahedron, this red one and the cyan one, and you just overpose them together to make 8 vertices. That's how you can naturally extract the qubit structure geometry from the qubit, right? But this kind of scale was somewhat arbitrary, and I didn't actually tell some specific meaning of that cube, well, because I haven't realized it until recently. But it's actually a nice representation for how you can represent those vertices together, not just separate two tetrahedrons over, like just overposed over each other, but as an actual separate entity, right? So in this kind of pictures, I always draw like block sphere acts as a banana for scale, right? So any kind of object or a vector essentially has to be represented in that picture in relation to that block sphere. What I mean by that is just if you have a matrix, like SU2 matrix, like a complex matrix 2 by 2, you have to normalize it so that its diagonal trace, sum of the diagonal is 1. So that's how you can scale it up everything. Whatever object you have, you can probably make it in that particular geometry, make it into a density matrix, normalize it. That's how you can compare things to each other, right? And so a different kind of scaling, well, first of all, the cube is kind of already appears, stares you into face for this picture, right? When in just one.
Nick, can you give me and maybe some people in the audience who haven't seen this before, like a quick rundown of what we're looking at?
So, well, you see, we obviously have a block sphere inside of it. This is just the main object, quantum object. Is just a geometric space of all possible quantum states over two complex amplitudes or whatever, right? Your minimal finite dimensional quantum state. And block sphere represents the geometry of all of those states, right? Any point on the block sphere is a valid quantum state. You can, whenever you have a tetrahedron like that, when you just wrap around that block sphere so that now it becomes an insphere, that's a natural choice of basis, minimal choice of basis that you can just map your density matrix into and represent it as a probability vector. So now it's a, before it was a element of Hilbert space as a density matrix, but choosing these 4 vectors and the vertices of a tetrahedron, now it's a probability vector, just 4 real numbers summing up to 1, right? It's a tetrahedron because it's essentially a simplex from 4 dimensions projected to 3. So that's what you're looking at. So just a choice of basis.
So you say it's four real numbers adding up to 1.
Yes.
And that's why I have a 3-dimensional space?
In a way, yeah, because it's 3 degrees of freedom, the same as a density matrix, because Hermitian density matrix. It has 4 complex numbers. Well, it's real on the diagonal, right, summing up to 1. And because it's Hermitian, your complex variables on the off diagonal is also related. So you have 2 complex numbers on one diagonal and 1 on the diagonal, right? It's also 3 degrees of freedom. So you can just convert from one to another. It's just a linear map. So that's how you can naturally convert it to a probability, not even quasi-probability, right? But it's not, well, some people still say that it's a quasi-probability because it doesn't have a nice property that your Pauli projections and measurements are not naturally a marginal probability of that vector or whatever.
You have a quantum probability, which is like two complex numbers, right? On this block sphere. Or is it a ratio of them?
It's not a ratio. It's usually you have a quantum state, well, like this, right? It's just some vector with 2 complex numbers, right? For your 0 and one gets, right? Your usual Born rule tells you how to compute probabilities from these complex amplitudes by absolute squaring them, right? Those numbers, right? You just take, that's how your Born rule usually works. Take your amplitudes, take the absolute value, right? And square them. And those things would be probabilities. In that particular basis or observable that you chose. In this particular observable is just an axis from 0 to 1, just from South Pole to North Pole.
So the amplitudes add to 1? Or the amplitude
squared.
squareds?
Yeah.
Okay.
Yes. That's when your actual state in that representation is normalized. You normalize it by its amplitude squared has to sum to 1. But you can also do it for the density matrix. And density matrix normalizing density matrix means your corresponding diagonal is just gonna sum up to 1. So it's basically the same probabilities of those. Right. So you can just take the diagonal of the density matrix. But what I
yeah,
okay,
so I guess that's the trace then. Is it? Is that what the trace
the
is?
trace, yeah, the trace of the density matrix, the normalization, yeah. You normalize the trace. For arbitrary density matrix, you normalize the trace. That's how you plot it on the block sphere. It's like if you have this random thing, right? It's a pure state, so it's pointing on the surface. But if that state was mixed, again, it's gonna be pointing somewhere inside the surface. But its trace of the underlying density matrix is still gonna be the 1. That's how we compare them together, right? But that's like the basic geometry. But it's like, what's the point of that feature?
And then you're taking the quantum state, and then you're just reading off the components, and that's what the tetrahedron is from. So you have a constraint on those 4 real scalar values.
It's almost reading out the components. I'm reading out the density matrix in its maybe flat form. But if you just flatten the matrix, right, it's 2 by 2. If you just list out all its components, this is like you just vector, but then you change the basis of that vector by some linear transformation, essentially. You can just dispose of every imaginary numbers in there, and it's going to be represented by just a probability vector. If you do it right by choosing this basis, it's going to be just a nice probability vector because it's a regular simplex, and that's the geometry of all probabilities. Right? The actual basis, you can, if you look at it, they have this basis here. And that's the matrix that you multiply it with in order to turn this density matrix to its probability form. Just a linear transformation. You can choose a different basis. They have different properties. I want to just like show some geometry where there's some intuition about this particular basis, because if you just stare at it like maybe from a few angles, I labeled them. You see that they are pointing right in the middle of three orthogonal bases. There are 3 natural orthogonal bases for the qubit, because you have a 3D geometry, you have 3 axes, right? Up, down, left, right, like forward, backward, whatever. Usually it's called 0, 1, plus, minus, L, or left, right, right? Yeah. So every vertex of a tetrahedron pointing inside, it can be naturally labeled by 3 of those. So it's a pair, so it's like a triple of choices of 2, right? So it's like a binaries, triple of binaries. So it's already kind of suggestive enough to make it into a cube. And obviously, you can add another tetrahedron, because it's not enough to make because it's not listing all possible combinations of those binary variables into triples, right? And yes, right, you can actually make a dual basis for that tetrahedron. It's just inverting it out, and they're not even connected by any rotation. So it's an actual like reflection of one tetrahedron to another. So we can't orient one to another. So that's why it's dual. And you can label its vertices by whatever the left combinations of those binary variables left. So you just in the end you end up with 8 vertices like this, and you can of course make a cube out of those like this. So that's essentially a bit rescaled version of the cube above, right? But now, okay, so that's how the
So
same.
wait. Can you go one step before that?
So the dual basis, right?
Right.
So you
Right. So, sorry, continue. I need to make some notes.
so we had this natural basis, probabilistic basis for qubits, right? So that, but geometrically speaking, this tetrahedron has its dual, so that you can reflect all its vertices around, like an actual put a minus sign or parity transformation, if you wish. You invert all those vertices, or you can just equivalently just swap any pair of vertices and do some orientation. That's how you can make a dual. And you can label vertices of that dual tetrahedron also with the same kind of triples of this poles on the block sphere, right? So that it's pointing exactly right between those three. And now we kind of have this. You can already see it just on the block plot without any tetrahedrons. You see that's like great circles. They form this like 8 triangles, and those exactly would correspond to 8 cube vertices. It's like you can just stretch them out, right? So that's where it comes from.
So those 8 triangles are basically the 8 sectors of a
yes,
coordinate axis, right?
Yeah. But here is just it's better to think of them as just as vertices, right? In between. But anyway,
Right.
so we made this qubit. So so now it's a natural question how we can combine this, because with the single tetrahedron we had a single probability vector, just 4 numbers, which is equivalent to a density matrix. So we can recover one from another. But if we combine them together, like 2 probability vectors for both of those tetrahedrons, you can make 8 numbers, right? You can make 8 numbers together, and you can reshape it into 2 by 2 by 2 tensor. Okay, so that's what I do here. So we form this basis. This cubism C corresponds to, for example, like this tetrahedron, whatever it is. It's conjugate basis. It's like taking the dual. It's for another one, and you basically do the phase space transformation, recover the corresponding probability vectors for that particular random density matrix that we use. So we have these 2 vectors now.
Sorry, when you do conjugate basis, are you literally taking the conjugate of the component vectors?
Yes, actually, yes. It's literally if that matrix over here, the one that used for the linear transformation, you can conjugate it, and you get geometrically the dual of that tetrahedron. It may be like the ordering of the vertices is going to be screwed up, but those will be the vertices. Can maybe reverse them or something like that. So what you can do next is, okay, we know that we have those 8 vertices on the cube, right? You can enumerate them by some combination of binary, well, not binary combination, my 1 and -1 triples. I basically extract them from the corresponding block vectors here and take the sign. So if you see here, if you just join those elements of the basis and its conjugate basis, there are in total 8 elements, and compute the corresponding block vectors for those. It's going to be the vertices of those tetrahedron, right? The vertices of that cube over here that forms this. The vertices of this cube, right? So they have some components, but we can ignore the components, just focus on the sign of those. Right, so you can compute those triples, but you also know that the natural ordering of the vertices may be this one. So we can just just walking around in binary across all the cube vertices and just find the permutation so that you can relate one transformation to another. So we can relate how this Cubix relates to this ordering. And this ordering is actually, I found it, for me, it was kind of arbitrary why this particular ordering works. I was actually found it by enumerating all of those because I wasn't sure because I was searching for a particular property of that 2 by 2 by 2 matrix, which I actually construct here. And that's where the Cubix come from, right? So we just join this two vectors in one basis and another basis. I just join them together, divide them two so that it's normalized again. So that if I just sum all the numbers together, it's still one. So it's just a probability vector, and just permute them with that permutation and reshape it into 2 by 2 by 2 matrix. So it's now it's an actual Cubix, and we can put them into vertices of a cube, and then we have some interpretation of the actual vertices as some kind of numbers. And the interpretation is very nice. So it's Cubix, all the numbers sum up to one, but because we chose this particular ordering of those, if you sum or I guess reduce or trace out any of those particular dimensions out of those three in pairs, you can recover all the Pauli probabilities. So in a way, you can the Cubix naturally stores all the measurement results in all those three bases x, y, z. So this is like it's like a joint distribution over those, but a little bit more expanded, or you can say shrinked. It's what I know, Karas, maybe you don't know. It's like I was last time couple of times I was thinking and trying to explain this notion of expanding your probability vectors or shrinking your bases, and that is how it corresponds to inference and all that. But you just think about, because we chose this large basis that completely envelops your block sphere, so that it becomes a probability vector, while it's still sometimes considered as a quantitative probability vector, you can't really recover your probabilities for your projective measurement, like actually what people usually do when they measure the qubit. Maybe if it's a like polarization of your photon or the qubit spin, and you measure it in some orientation, you just and do some statistics on those. It's not the probabilities that you observe. So it's not just you can sum up, marginalize this probability vector and recover those, but they are related. And they're related because with this single expanding transformation, you have to transform your probability vector a little bit. It's equivalent to shrinking your basis. So you have to make your block sphere kind of go a little bit outside of your cube. It's like here, I have this. It has to poke outside of the actual basis so that it becomes a normal distribution that you can actually recover your measurements. All right. So that's where the negative probability is coming from, because as soon as you shrink your basis, your representation in that basis can have negative numbers, because it's now it's pointing outside, right? It doesn't completely cover it. So that's how the negative probabilities appear. But these negative probabilities allow you to have these natural marginal distributions by just like summing over some of the dimensions of that Cubix. You recover x, y, and z projective measurement results. Something like that. Or you can just use this maximal basis and consider that you have to, after you marginalize your distribution in the Cubix, like sum up some of the subset. Maybe I should show it as an example. So we have this Cubix. So I could maybe just explain what's happening here in more detail. So here it's all the possible pairs you can take and sum over your dimensions, right? For example, if I reduce this Cubix over first and second dimension, you get just two probabilities, right? But it's not quite, because I sum of the over essentially over x and y, so it should correspond to the measurement, whatever the corresponding measurement is in the computational basis. It should correspond to this one, maybe up to somewhere into, maybe we'll just make it explicit, make it to z basis, which is the same. It should be only the same, but up to this expansion, right? So you have to modify it a little bit. What I'm doing. Is it not? Wait. Now for some reason, math doesn't agree with me. Okay, let me just evaluate everything, just in case. I have this. I have permutation. This is the Cubix. Okay, now they match. I don't know why it didn't match before. So essentially, the probabilities of measuring this qubit in Z basis are the same as just reducing this particular qubit, like computing the marginal and expanding it a little bit, or reducing the basis. And you can, that's basically the Cubix collects all the probabilities. So it knows about all of them in a natural way. But you can also do the quasi-Cubix. That's what essentially this picture is is all about. And I have a little conjecture about it, which kind of, I don't know what to think about it yet. If you pre-expand the Cubix, which is essentially what I mean by reducing the basis, so that you make your fully enveloping cube of the block sphere to this one, right? So that your, I don't know, what is this? I don't even remember. So you pre-expand it. I don't know, whatever it is. So this is like for arbitrary, this is like everything put together. It's like take a random state. Maybe it's some arrow on the block sphere. Compute its probabilities in one basis and compute it in its conjugate basis. You make a Cubix out of it. You expand the Cubix to make this quasi-Cubix, which is essentially this 2 by 2 by 2 by 2 by 2 by 2 tensor or array, right? And you plot it like this. And the little conjecture here is just the negativity, which is what most of the people consider as the actual quantum metric or some kind of measure of quantumness that quantum states occupy, is always gonna be across some edge or a vertex, right? And it can also be zero if you choose like one of the vertices on these poles. So if you want, if you pick zero, it's gonna be zeros, like across the whole plane. But for random arbitrary states, the negativity always going to be appear on one edge. So there is a negative. It's restricted in negativity. So that's like a little conjecture about this construction. But that's essentially what. That's all. That's what this whole construction is all about. Very simple geometric thing to put together and make a Cubix that relates to projective Pauli measurements, and that's it.
I really like the idea of having a geometric interpretation or visualization of trying to comprehend like these quantum physics, or how would you even describe it? Quantum probabilities, quantum states. It kind of allows you to work with these things in your head a lot better than any other way it's currently taught. So I just wanted to mention that it's awesome.
It's indeed, it's like, for some reason I tried it very hard to find nice picture in all the papers about like quantum information. Even like papers titled quantum geometry, qubit geometry, it's like a couple of pictures more. I don't know. It's not enough visualization for even geometric topics in the literature. But
it could be useful for education, maybe. A lot of people wanting to bring quantum, like teaching quantum to a high school level. So having these kinds of visualizations might make that practical. I don't know. That's just my 2 cents. It'd be cool if that happened.
For example, one of the things I realized is how to connect this idea of these two dual tetrahedrons to the notion of how Hilbert space for qubit SU2 relates to the space of quaternions and the space of all possible orientations in space, right? Those are 2 different groups, and there's the popular narrative about it that it's like the SU2, the space of all possible quantum states, essentially, or quantum rotations, unitary transformation, double covers the space of all possible rotations, right? But this relation that you have to reflect your tetrahedron or swap some vertices so that to make it dual, so that they're not related to each other by this actual rotation. It kind of brings this idea of double covering and this duality, that there are two possible things that correspond to the same orientation, right, in this space. It kind of makes it more clear. And I was wondering that one of the questions I have is like how that generalizes to higher dimensions, for example, right? Because you can make a Cubix, it's still a Cubix, but not for a qubit, but for a qubit. But now it's going to be a Cubix of dimension 3 by 3 by 3, right? Because now, but you also, in order to make this Cubix, you have to make two transformations. Here we just took a conjugate of our basis, right? We just took a dual of a tetrahedron, but in that high dimensional case, you have to do something else, like a third thing. Like you have to make some triality or three transformations, natural things to think, natural way. Natural transformation may be just some kind of rotation by 120 degrees. So this kind of duality kind of relates to just 180 degrees rotation plus some permutations, because you can't really orient it. But in that higher dimension, you have to do the same kind of thing, but rotating 120, so that you can do 3 of those to turn it all the way back to its to the initial state. And I was trying to do it, it didn't work. So like I was trying some naive things.
Well, so I mean, what's chiral? I mean, the way that the vertices are colored on these tetrahedrons makes them chiral and makes them unable to be rotated into each other. Is that true?
Well, you can rotate one of, you can, like, for example, I think I had some
there's a symmetry between tetrahedrons, but there's not the way, I think, the way that the vertices are colored.
Well, vertices are colored like this one is the dual of this one. So the same color means
so
the
inverted.
dual. Yeah, so you here just inverted them. Okay. But if you, for example, will try to orient this color, like if you're gonna try to match all the colors by just rotating, you won't be able to do it.
Right, because in 3 dimensions, inversion through the origin flips orientation. Yeah,
it's like a flipping one of the pairs of vertices, so it's like a odd permutation, right? So you won't be able to.
I mean,
but a cycle,
the same thing won't work in 4 dimensions. Is what I'm saying. Like that's multiplying by -1. Is not a orientation reversing operation in R4. So
yeah,
if you were trying to like go to a higher dimension and do the same thing that you did here.
Yeah, conjugation is not going to work. That's clear, that just reverting it, the vector, whatever that it is in the higher dimensional case, it's not going to work. But I was saying that maybe a rotation plus something else, like rotation by 120 degrees. So you have rotated once, rotated twice, so that you have 2 transformations of your bases, so that you can have 3 bases in total. I was trying it here, but I'm gonna go back to this thing too. But I think I was trying it like for Qubit. Here essentially like what I would try. I know it's just a mess here, but here was my idea. It's like if you have Q elements, you rotate it by pi over 2. Guess it might be pi over 3. Okay. I was trying stupid things here. So this is like 2 different bases, and you make essentially the same thing. Now this is a Q treat. Now you have 3 vectors, which are now not 4-dimensional but 9-dimensional, 3 squared. You combine 3 9-dimensional things into 27-dimensional things, and now it's a 3 cubed, right? So you can that's a Cubix 3 by 3 by 3. In a way, like this thing, right? And it was and the goal was to do so that this
wait
again marginals would work the same way.
You're saying you put everything in 27-dimensional space, or that you have a 3 by 3 by 3 matrix array?
Yeah, so 3 by 3 by 3, it's 27.
Yeah.
So it's a Cubix, and I constructed it by just 3 9-dimensional probability vectors. because 9 dimension, it's what it's what your
Yeah.
Qtreat have. It's what the embedding dimension of the simplex for the Qtreat. Here they have a 4-dimensional one, which was a tetrahedron, a simplex in 4 dimensions, 3-dimensional simplex in 4 dimensions. For Qtreat, it's going to be 8-dimensional simplex in 9 dimensions, right?
Mm-hmm.
So the same kind of thing, but you have to compose 3 things together in order to make the same kind of Cubix. And my goal was to recover the same marginal probabilities of measuring essentially spin orientation in 3 different dimensions, in 3 different orientations. So in this kind of basis, right? And it didn't work, like naively. Maybe there's still a way to fix it, but I'm still not sure whether it's gonna work or it's just stupid in some way. I don't know. Right. And then
So
I'm
Yeah,
only
yeah, go ahead.
slightly confused.
yeah, I'd like to go back to like the starting point, basically, just to make sure I understand what's going on here. So,
Mhm.
so let's try to, because I've never really worked with quantum mechanics that much. I mean, obviously, I learned everything when I was a student, but it's been a long time since I actually kind of exercised my quantum mechanics. But I'm sure that with your help, we can understand exactly where this Cubix is coming from, like formally. So the first thing that comes to my mind in your description is that so these quantum states, these are density matrices, right? And they are
Mhm.
unit trace Hermitian matrices, right?
Yeah, right.
So yeah, so in the case of C2, right, like 2 complex variables, so the smallest matrices you can have, they're characterized by 3 real numbers, right?
Yeah.
And that's this whole business with the block sphere and like the tetrahedron and so on that you're describing, right?
Yeah, in a way, yeah. You have 3
So-
degrees of freedom.
Right.
Wait, so is
So
the block sphere, is it the interior is included? Is it the volume
Yeah.
of it? So kind of like,
it is,
Yeah.
right?
Here it is included. You envelop the block sphere completely with this basis.
Like
So
the,
that
the block sphere proper, not the ball, is just the pure states, right?
Yeah, right.
Yeah.
But you can
So-
still do the same kind of thing for the mixed state, so for the interior of the ball too.
Yeah. So my point, so how wrong is it to say that your Cubix is simply the 2 matrices put together?
Well, in a
Right.
way, I don't know. Well, why would be which matrices exactly? How do you
Well,
recover?
the quantum states, right? Like the density matrices.
Yeah, but up to reshaping, yes, but it's not like they correspond to a face of the cube, right? It's like not 2
No.
faces of the cube stacked together. It's the corresponding vertices of the tetrahedron, so it's not just stacking. It's like putting them together and do some reshaping of those.
No, of course. I mean, I'm saying, like, because when you say you have these 2 tetrahedra, you're effectively saying, I want to take 2 Hermitian matrices, right?
Yes.
So a pair of Hermitian matrices, when they are 2 by 2, is exactly a Cubix, right?
Mm-hmm.
It's a
Yeah.
It's a complex Cubix. I mean, it's not maybe not a Cubix in the sense that you are implying later. That's not what I'm saying. But we have the moment that you say, hey, I want to consider 2 quantum states in this density matrix representation. We have, informationally speaking, we have a Cubix specified, right? Complex Cubix. You agree?
Yeah. You still have the same amount of information. They're even related to each other. Those 2 density metrics, and they are linearly related.
Are they related?
Yeah, you can still. It's just basis and its conjugate basis just related to some linear transformation.
Oh, wait, but then, okay, that's different. So, because you said that you were doing a mix, right? That you're,
Well, in a way, I'm just composing them together in order to recover all the measurements from that Cubix directly. That's all.
Wait.
But you
Wait.
still have the same number of degrees of freedom. You still have 3. It's like 8 numbers, but 3 degrees of freedom.
Okay.
It's very overcomplicated.
Okay. I see. Sorry. Yes. No, that's different. Okay, that's very different. Yes. Sorry. You see, these are the right question for me to understand what's going on. All right. So you're taking the one quantum state, then representing the in this particular tetrahedron of your probability space, right? And then you're basically embedding in the same space the conjugate expression, right?
Yeah, I'm embedding the same density matrix into a conjugate basis. The same
Yes.
density. Yes.
Right. So I see. Interesting. Right. Okay. I think I understand what you're doing. Okay. So let me. I want to understand how we get to a Cubix, because right. So yeah, that clearly doesn't seem right what I was saying, right? Like, it's not that you have the two Hermitian matrices and you put them together, or maybe it is. Because one is the complex conjugate of the other, right?
Well, not quite. Well, here it is, right? It's like a different. I don't even have. It's not really the density matrix that we're comparing, right? In a way, it's the same matrix, just up to some different bases, right? It's like what we are doing here. Let's explicitly see what's happening. So we have a density matrix, right? We just normal it, flatten it. So we have this complex vector, and then we just take this matrix and multiply it by it. Or maybe you have to do the inverse. Sorry.
Wait.
Okay.
You flattened?
So yeah, I flattened it like so. It's like a vectorization of the density matrix. That's what people calling it, right? You just treat all the elements of the 2x2 complex matrix. Oh, trace one here as a vector.
Yeah, as a vector. Yeah, sure.
Yeah. So that's how these numbers are recovered here, right? So that's the same as that's what I call the phase space transformation. That's how your quantum state looks in phase space. So now we have a distribution or quasi distribution. Right, and you do the same thing with the conjugate. You get these numbers. And if you want to know how they're related, obviously you just do some matrix inversion. So what can we do?
Okay, I see. Right. So this is interesting because, so the space of the space of Hermitian 2x2 Hermitian complex matrices is 3 real dimensional, right?
Mm-hmm. Yeah.
But it's yes. Still a vector space. Wait. How's it? It's kind of confusing, actually.
So that's usually what quantum, all the quantum stuff brings.
No, but wait. No, I'm just confused by linear algebra. This can be quantum.
Okay, that can be.
Although some people say that quantum is just linear algebra, but
Yeah, it is. In a way, yes.
no, but wait. It can't be a what is three-dimensional is not the subspace of Hermitian matrices,
What do you mean?
right? Because you need four different quantities. Right, it becomes okay. It's so the unit trace is what makes it three real dimensional, right?
Yeah.
Okay. So that's okay. That's not a linear space. That's some kind of affine space. Yeah, it's not a vector subspace. Because I mean, I was very confused because I thought, I mean, if you define your vector space with complex vectors, right? This is a complex vector space, right? Like the space of Hermitian matrices. How is it possible? And it's clearly a sub-vector space of the vector space of complex matrices, right? It's not possible that that sub-vector space is three real dimensional because it has to have even real dimension because it will be integer complex dimensional, right?
Well, let's see. So if you transpose it,
And this-
it has
But
to.
this is my
they're
confusion. This
conjugate, right?
is not a problem. we shouldn't
Well,
be.
hold on. No, on the diagonal, those have to be real numbers, right? Because they have to equal their conjugates.
Yeah. So you have
and then the off diagonal, you just have like one entry for a 2x2.
yeah.
So that's
Mhm.
two real numbers and a complex number.
Yeah. So
Um,
so that is a four-dimensional.
And trace one restricts one of those real numbers on the diagonal.
oh,
Yeah.
okay. All right.
I know. But what I'm saying, it's clear. It was just my confusion for a second that I was not. I mean, trace equals one is not a linear relation. It's an affine relation, right? Because it's putting the components equal to one, right? Not equal to zero. Like the trace equals zero trace equals one is a non-homogeneous equation, right?
Right.
It's not linear.
It's like
It's
a
affine.
subset that doesn't include the origin. It's not a linear set.
Exactly. It's an affine space, right? It's a affine subspace of that.
Right.
And I was very confused for a second, and the reason why is because you know that the Hermitian matrices are a complex vector subspace, right? They form a complex vector subspace. So if you know that, and it's finite dimensional, obviously, so you know that its dimension is an integer for complex numbers, right?
Hmm.
So that means that for real numbers, it's going to be even dimensional, right? Because all vector spaces, all complex vector spaces are real vector spaces of double dimension, right?
Yeah.
When you put things back into a basis and all that stuff you want.
Mhm.
But anyway, so that's clear. But so okay, so how do we get to? I want to see how we get a Cubix. I want to because I mean the moment that I see how Cubix is formed, then we can do a lot of things with that. But I mean, we can do a lot of things with them, but I want to understand if any meaning can come of it. So you have the two states, the one state, and then you represent it in both.
Uh-huh.
And you're saying that you're embedding both representations, the conjugate and the direct one, in the same three-dimensional space, right?
Well, not embedding them. I'm just. Well, they're already embedded. Like each number, each element of those representations already correspond to one of those vertices, right?
Right.
So just putting them together, so that now I use all of the 8 vertices to representing this representation, this 8-dimensional representation now. Like,
Well, but what I mean is that So if you show the picture, like the graphic that you had, right? The first tetrahedron, just one.
Okay.
When you showed only one tetrahedron, right?
Yeah.
That is an R3 representation of like that tetrahedron, right? Like that subspace of R3 is like your set of quantum states, basically, right?
Well, the block sphere is a sub. This is like the space of all probability distributions.
Okay, sure. Yeah.
Yeah. Mm-hmm.
Yeah. Fine. Yeah. So then if you're embedding, so okay, like this three-dimensional space contains the representation. I mean, it's going to contain a unique point in this space will represent a unique quantum state, right?
By that space, what do you mean?
Like the three-dimensional space that you're rendering there.
Like every point, even outside of the tetrahedron or what?
Well, not outside, because outside it won't be a probability distribution, but inside of the tetrahedron at least. Like,
Well, inside it. Well, if it's inside the ball, it's a valid quantum state. If it's inside of tetrahedron over here, but not outside of the ball, it's not a valid quantum state, but a valid
okay,
probability distribution.
it's a probability distribution, but not a quantum state. Sure.
Yes.
Okay.
Yep.
So what I'm saying is that if you then superimpose the other tetrahedron, right?
Right.
Yeah. I mean, the way I understand that is you change your base in your complex variable space, right?
Literally, I would think it as a phase space. It's like nothing complex about it anymore as soon as you go to geometry.
Well, no, but we have to. I mean, we're doing something like this is in a way a projection or some kind of dimensional slicing of something that is higher dimension, right? Like,
well, simplex itself, its embedding dimension is 4, right? Because it's just it's just made out of like rows or columns of the identity matrix, right? So this is like 4-dimensional points that form this simplex, and this is just its 3D projection.
Yeah.
So
this is what I mean. So that's true for one simplex, one of the tetrahedrons, right?
Yeah.
But if you put the other one and you embed it in the same space, so you're making a construction that is spatial within the same space, right? Like these things are sharing space. Like they have some surrounding R3 that is kind of like supporting everything, right?
Yeah.
So in that case, you need to. I mean, there is an interpretation of. I'm saying something that I think is quite trivial, so I'm just trying to double check with you that if you have your Hermitian matrices representation that you can conjugate, right?
Mm-hmm.
That is an internal transformation of your space. It doesn't. It is just an involution in your space, right? Like you can move things around, and you just if you do it again, you get back to the same place, right?
Also like a reflection, if you think of in this geometry.
Yeah, like a reflection. Yeah, it's some kind of generalized reflection. Yes, it's like an involution, right? An involution is some kind of generalized reflection. You apply twice and you get back to the same
Here
place.
it's literally a reflection. It's like conjugating your density matrix means you're just reflecting it in like across the y one of the axes, essentially the y-axis. It's because the Pauli matrix only one of the Pauli matrices has complex dimensions. The second one, Pauli y. So if you conjugate your representation, that's the only thing that gets flipped. So it's like reflecting across the y dimension, the y-axis.
Sure.
Yeah.
So yeah, so okay, so that's exactly what I'm trying to say, right? Like that the operation of conjugation in your complex matrix representation turns into in this case, as you said, a y-axis reflection in this three-dimensional space. Right? So what that means is that the interpretation of all the points in that space, a priori, each of them uniquely correspond to some Hermitian matrix or some complex matrix, maybe not Hermitian, but some complex matrix. Right?
Yeah.
Okay. All right. So what does it correspond to in matrix language when you say, I'm going to take this state, I'm going to reflect it over y, and I'm going to average it, right? Because you take the average sum, right?
Kind of. Well, not summing them, just catenating them, just opposing, right? Because you are making.
What is that? You're catenating them.
Well, it's you have two vectors, four-dimensional vectors, right?
Sure.
I make a single one which is eight-dimensional. So
Okay, then
not,
okay, so then yeah, but that's where I'm going. But this is slightly different because there is a so this is doing a product, right? Like this is really two orthogonal or at least two what's the word? Transversal planes, right? Four-dimensional planes.
I guess. Okay.
That are being projected down to 3D with these shapes, right? Because those four-dimensional planes have some subspaces that are the probability one, and then those two are intersecting somewhere, and then when we project them down with this representation, they appear as these tetrahedra that are like overlapping in our three-dimensional space, right?
Yeah. Well, in a way, it's in 4 dimensions, those are the same space. Maybe just the projections are different, how we project them, right? So that they are not related by 3D orientations, but it's still the same 4-dimensional space that we are projecting to 3D, but their projections are not related by orientation. So that's why they dual to each other, and that's why the basis is dual.
Yeah.
Because in 4D it's still a simplex. It's just like these four things, right? And that's how simplex looks in any dimension.
Sure. I mean, I'm very fascinated by this structure because I mean it is not directly related to QBCs, to all this Cubix business.
Yeah.
But this structure over here, like this double tetrahedron, it's a very interesting thing. So I kind of, I mean, I don't want to say discovered, obviously this was not a discovery, but like I found this structure when asking if you could have a set of three vectors a set of six vectors that were that added up to 0 altogether, right? But that did not add up to 0 in pairs or trios.
Okay.
Right? So if you think about it,
that's the same thing, right? That's the pair of tetrahedron or what? Or
I think so. Yeah. So I'm stating this problem in this completely different language in case it actually makes some sense here, because
so that's 0, right? And
that is 0.
We've got another minute. Yeah, I don't know if you want to quickly wrap up. Or yeah.
None of those are 0.
Yeah.
Right? And if you do the two opposing threes, same, right?
Yeah.
So, right?
Yeah.
So it's kind of an interesting structure, right? So we should definitely do some kind of follow-up on this, because I found this structure in a completely unrelated question, right? Like completely unrelated, nothing to do with this. It had to do with like commutators and ternary commutators and all that stuff.
Well, this structure is just a cube. right? So on its own, it's just a convoluted way of describing a cube.
Well,
why is it
not exactly a
double
cube,
cube?
right?
All right, Ken.
It's not exactly a cube.
All right, cool.
James
Thanks,
and I
guys.
have
That was
to
an
have
awesome
to
stream.
go
Yeah.
on a different meeting with Steven. So,
All right.
Well, maybe
All
it's
right, yeah,
gonna
yeah.
late for like half an hour. Okay.
But Nick, are you going to that meeting as well?
No, I think I'm not.
So
It would be cool
so
if you
let-
can join.
let's
Yeah, the Zoom link won't keep us on here, but yeah, I think we should definitely follow up with this.
Yeah,
Yeah.
Great.
I
Okay.
still
follow
have
up,
like
huh?
thanks for everyone on the live stream. See you guys later.